The subterranean nightmare of the assembly lines was only half of the crisis, for even if an airframe could be successfully rolled out of the dark mountain tunnels, it was still a heartless metal shell without its complex power plants. As the war entered its final, desperate year, the German industrial machine faced an absolute strangulation of its supply lines, resulting in a catastrophic shortage of the rare, strategic metals required for advanced aerospace engineering. The Junkers design team had originally engineered the Jumo 004 jet engine to rely heavily on nickel, cobalt, and chromium, which were essential for creating the specialized heat-resistant steel alloys capable of withstanding the volcanic temperatures inside the turbine chambers. However, with the rich mines of the Balkans and Scandinavia cut off by the advancing Allied armies, Germany ran completely out of these critical materials, forcing the engineers at Dessau to make a tragic, highly volatile compromise in metallurgy.
Faced with an impossible dilemma, the engineering team had to redesign the spinning turbine blades out of ordinary low-carbon steel, coating them with a primitive ceramic glaze to prevent them from instantly melting under the intense heat of burning synthetic kerosene. This forced modification transformed the Jumo 004 from a triumph of modern science into a terrifying, unpredictable liability for anyone who climbed into the cockpit. The lack of proper heat-resistant alloys meant that the internal components of the engines would rapidly warp, stretch, and degrade under the immense centrifugal forces of high-speed flight, a phenomenon known to engineers as metal creep. Because of this structural volatility, a brand new jet engine had an operational lifespan of only 10 to 25 hours at the absolute maximum before it suffered a catastrophic internal explosion or a fatal compressor stall, requiring the ground crews to completely dismantle and rebuild the power plants after nearly every single combat mission.
For the young, inexperienced pilots assigned to fly the Me-262, this metallurgical crisis turned the throttles into levers of life and death, requiring an agonizing level of delicate handling during the chaos of aerial warfare. If a pilot slammed the throttle forward too quickly to escape an enemy fighter or to pursue a bomber, the sudden surge of fuel would create a massive thermal spike that the cheap, compromised steel blades could not handle, instantly melting the turbine or causing a catastrophic engine fire in midair. The entire weapon system was constantly operating on a razor-thin margin of safety, where a single millimeter of throttle movement could mean the difference between achieving supersonic glory or being incinerated inside a flying blowtorch. The brilliant, forward-thinking aerodynamic design of the Stormbird was fundamentally trapped inside a crumbling industrial reality, a masterpiece of physics built with the makeshift materials of a collapsing empire.